Okay, thank you. I think it looks like my presentation should be loaded, so I'll get started. The title of my presentation is Analysis of Parameters Influencing Horizontally Curved Steel I-Girder Bridges During Construction. First, just a little bit to go over the background and the problem statement. This is actually a research project that I worked on. Horizontally curved steel I-Girder bridges often experience problems during erection. Currently, there's no specifications for erection procedures and or techniques. A lot of codes have been updated in the past few years to include sections that state how important it is to analyze your curved girder structure during construction and make sure you're aware of any possible unwanted stresses or displacements that could occur during erection. But the codes don't provide any specifics about how you should actually construct bridges. So the current study was created to examine a number of different types of curved steel I-Girder bridges to determine the influence of different parameters on deflection during construction. So next, I'm going to briefly go over the scope and the task of the research. Throughout the presentation, we'll step through each of these in some more detail. The first step was to create a finite element model of Bridge 207. And Bridge 207 was actually field tested throughout the entire construction process. Whenever the steel girders were fabricated at the steel yard, they are instrumented with strain transducers. And throughout each step in the construction process, those transducers were monitored. So we had a vast amount of field data available for Bridge 207. So we're going to create a finite element of that and then compare those model results to the field test results. The next step in the process was to design 30 base bridges. And then we would analyze these base bridges using our finite element modeling technique. And we would locate areas of maximum displacements during construction in these bridges. And the next step was to use an analysis of variance to analyze the displacement. And then finally, in conclusion, we want to determine the influence of our different parameters on the deflection. So next I'm just going to go into the structure description, and this is once again Bridge 207. It's seen there in that picture. Like I said, this bridge was field tested from when the girders were fabricated until finally when the deck was put on. It's a two-span continuous structure. It's composed of 5 grade 50 steel plate girders. The girders are spaced at 10.67 feet. It has a radius of curvature of 1921 feet. The cross frames are composed of WT sections, and the testing of the structure was actually conducted by someone else, Jason Shura, in 2005. So this next picture is just highlighting the instrumentation plan. All of the girders were instrumented with strain gauges. If you look at the plan view, section BB is located near the pier. We didn't put the instruments directly at the pier because we wanted to avoid any concentrated forces, but they were very close to the pier. The other sections that were instrumented were section CC, which was close to mid-span of the first span, and section AA, which was near about the quarter span of span 2. And all of these locations, you can see there's 2 different details. Detail 1, we have 4 strain gauges per cross-section. And detail 2, we only have 3 gauges per cross-section. And the reason we had to use 3 gauges in some of the locations was due to the amount of data collecting capabilities that we had. We didn't have enough channels to collect data for placing 4 gauges at each location. And you can also notice from the details that we placed the gauges on top of the bottom flange and then on the bottom of the top flange. The gauges were placed on the bottom of the top flange to prevent when they were pouring the deck and putting the deck pans on. We wanted to minimize the amount of gauges that were going to get knocked off during construction. So next, a little bit about the analytical program. We created a finite element model of Bridge 207. Our webs were modeled using shell elements. We actually had 18 elements through the web depth. This is a fairly small web elements, but our elements were actually approximately 6 inches by 6 inches. And this is a very detailed, more elements than you would usually need in standard design. But because we were trying to replicate what we were seeing in the field, we went with a very small mesh. The flanges and stiffeners were modeled with beam elements. The cross frame, same thing, beam elements, just open section ones because they were WT and angle shapes. We included the camber in the model, and the boundary conditions were replicated from those on the plans, and we also included any tie-downs or shoring that was used during the construction process. And the diagram there on the right is just showing the different components of our finite element model. Okay, so this slide is just showing the different construction stages. Because we were monitoring what was occurring in the field on this bridge throughout each construction stage, we needed our finite element model to correspond and look at each of the stages of construction. So that table there on the right just lists the different stages that we modeled in our finite element model. For example, for stage 1, girders 4 and 5 from abutment 1 to field place 3 were placed. And then in stage 2, girder 3 from abutment 1 to field place 3 was placed. So our model took care of this. Our model had all these different stages of construction. It first looked at that stage 1 where we only had girders 4 and 5 partially erected, and then in the next stage it dropped in girder 3 from abutment 1 to field place 3. And so on until we get to the final 3 stages are placing the slab. And the slab in this bridge was placed in 3 different sections. So all we were looking at it, since it was the construction model, is we applied the dead load for each stage, and we looked at the linear geometric response of the bridge. So this diagram graph is showing a comparison of the stage 8 section CC results. So stage 8 is the stage when all of the steel has been placed in the bridge, but none of the slab has been placed. So all of our steel has been erected, but we haven't poured any of the deck yet. And if you'll recall, section CC is located near midspan of our first span. So this graph is just comparing our field data, vertical bending moment distribution, to what we saw in the green on this graph is for our 3D finite element model. And then the blue is for a 2D grillage model. The 2D grillage model was completed by Shura, who conducted the field testing on this bridge. So we had results from a 2D model available, so we used those also in our comparison. And like I said, we're just looking at the vertical bending moment distribution throughout the section. And you can see along the horizontal axis, we're just looking at each of the different girders. And you'll see that we have varying results looking at this graph. For example, if we look at girder 2, location CC, our 3D finite element model is nearly exactly predicting the vertical bending moment distribution. However, if we look at girder 4C, you can see neither the 3D finite element model or the 2D grillage model are accurately predicting what we're seeing in the field. So this was typical. There are a number of different comparisons we did for different stages and the different locations that were instrumented. And we got varying results when we were looking at our moment distribution. So next we decided maybe looking at a more global representation of the behavior of the entire structure instead of focusing on a specific location with specific stresses. We thought we would look at the deflections to see if they would give us a better predictor of what was going on with the bridge. So this graph is showing the deflection results for girder 1, and we have the 3 things we're looking at again. The pink line represents the field data. A scan was conducted of the bridge when all the steel was in place, and then a second scan was conducted after the deck had been placed. So this deflection data represents the change in deflection from when we had just the steel and then from when we put the deck on. And then the green line is our 3D finite element model, and the blue line is showing our deflections from the 2D grillage model. So you can see the 3D finite element model is doing a very good job of predicting the deflections that were observed in the field for Girder 1. The grillage model is predicting the general shape of the deflections, but is not predicting the absolute value of them as accurately as our finite element model is. Now this graph is showing the same thing, but instead of Girder 1, we're looking at Girder 5. And you can see the same results. Both the 2D and the 3D models predict the shape of the deflection well, but the 3D finite element model is predicting the actual deflections of the structure much more accurately than our grillage model. Now the next thing we wanted to check, Bridge 207 does have a larger radius of curvature. It's about 1900, which is pretty large. So to also check the accuracy of our finite element modeling technique, we wanted to check something, compare to laboratory results from something with a much tighter radius to make sure we weren't missing capturing any behavior of our curved girder structures. So we decided to use a study that was done by Hines and Spates in 1968. They did an experimental study on a curved steel beam, and this steel beam had a radius of curvature of 50 feet, which is very tight radius, a span length of 30 feet. They used fixed support conditions, which resulted in a clear span of 27 feet. They actually enclosed the ends of the steel beam in concrete to make sure it was fixed. And they used deflection gauges, and this beam was tested under different point loads in different locations. The results I'm going to present today are from the case where they had a concentrated load at midspan. So this graph is showing the curved beam deflection results. The pink line is from the Hines and Spates experimental data. So this is what they observed in the laboratory when they were conducting this test. And the green line is from the 3D finite element model that was created using the same procedures that we used for modeling Bridge 207. So you can see, while they're not exact, that they're nearly identical. The 3D finite element model is capturing the behavior of the severely curved steel beam. So after we did the Hines and Spates comparisons and also the deflection comparisons with Bridge 207, we decided that we were happy with our finite element modeling technique. We were going to proceed to use that for our parametric study. So the parametric study involved 30 base bridges. They have varying parameters. We used different radii, unbraced lengths, span type. We looked at bridges with 4 and 5 girder cross sections. And there are 4 different construction parameters that we looked at. We were comparing inner to outer, which just meant placing the inner girder first and then continuing on until we erected the outer girder last, compared to starting by erecting the outer girder first and then moving into the interior girders. And the other thing we looked at for the construction parameters were paired versus single. And that just meant for the paired erection, we would be placing 2 girders at a time. And for the single girder, we would just be erecting 1 girder at a time. There are a couple of assumptions we made. One, we assumed that everything was 50 KSI steel. We assumed that all flanges were compact. We assumed the webs were transversely stiffened. And we did not look into having longitudinal stiffeners in our webs. So this diagram is just highlighting the different parameters that we looked at. The first, if you look in red, is showing the different span types we looked at. We looked at 3. We considered single span bridges, 2 balanced spans, and 2 unequal two unbalanced spans. So the two balanced spans had the span lengths of each span were equal, and the unbalanced spans, they were unequal. We also looked at having a 4-girder or a 5-girder cross-section. The 3 radii that we examined were 300 feet, which is a very tight radius, 650 feet, and then 1,000 feet. And if you see there in the yellow on the bottom, we looked at 3 different unbraced lengths, 22.5 feet, 18 feet, and 15 feet. And you should also note, if you look at this diagram, those 3 different unbraced lengths only applied to the bridges with the 300-foot radius. The other bridges that had a radius of 650 feet and 1,000 feet, their cross-frame spacing was controlled by the maximum that was allowed in the code. So those were set at 25. But for the 300-foot radius, we had those 3 different options that we looked at. So once we selected our parameters, the next thing we needed to do was design these base model bridges that we were going to look at. They are designed using the AASHTO LRFD bridge specifications. For all of them, we decided to use the same girder spacing and the same deck overhang. When we were designing these, we were really trying to limit, we wanted to keep everything as similar as possible, so we were only focusing on changing the parameters that we were interested in analyzing. We selected a slab thickness of 8 inches. All the radii and lengths that were listed correspond to the bridge center line. And we did these base designs using a 2D grillage model. So the picture there is just showing the 4-girder cross-section. We used an 8-foot girder spacing with a 4-foot overhang. So this picture is just showing an example of the single span bridge. We used a span length of 225 feet. This is for the 4-girder cross-section. We would have a similar bridge. We would just add a girder for the 5-girder cross-section. The abutment 1 bearings were restrained from vertical and transverse movement, and the abutment 2 bearings were restrained from vertical and longitudinal movement. All these bearing conditions were kept the same for all the single span bridges, have exactly the same support conditions. And this picture is just a quick look at the 2-span bridges. The top one there is the 2-span equal. So each span is 225 feet. And the bottom span is the unbalanced span. So they have different span lengths. The support conditions were kept the same for all of these too. Like I said, we wanted to keep everything as similar as possible so we could focus on the differences from our selected parameters. So once we had all our base bridges designed, and I should say these weren't designed to realistically be built. They were designed for obviously use in a research program. We didn't go through and maximize our flange size, efficiency, etc. We picked the biggest flange size that would work so that the bridge wouldn't fail under live load, and use that for the entire section. But that was done for all of the bridges, so they were all over-designed in areas by the same amount. So once we had all those designs done, next we had to go back and do our finite element models of them. So we used the same technique that we used for Bridge 207. Our webs were modeled as shell elements. We stuck with our shells were approximately 6 inches by 6 inches. So like I said, it's very small. The flanges and cross frames were beam elements. We modeled our bearing and transverse stiffeners with beam elements. We use shell elements for our slab. For the single span bridges, we assumed that the entire slab was placed in one step. For the 2 equal and unequal span bridges, we had 3 different slab placement steps for those. So this picture is showing a representative construction stages. So we had 30 base model bridges. For all 30 bridges, we had 4 different construction scenarios that we wanted to analyze. In the bridge shown here, we are showing paired inner construction. So if you look at the top diagram there, you can see girders 1 and 2 have been partially placed in stage 1 of construction. If you go down to the next diagram, we've placed girders 3 and 4 from abutment 1 to a little bit past the pier. Stage 3, we placed the remaining sections of girder 1 and 2, and then finally we complete the steel erection. So like I said, this is representing the paired inner construction where we place 2 girders at a time and we start at the interior of the bridge. We also looked at paired outer construction where we're placing, once again, 2 girders at a time starting at the exterior of the bridge. And then our other options are single inner, where we place 1 girder at a time starting at the interior, and single outer, where we place 1 girder at a time moving inward. Now for the bridges that had 5 bridges in the cross-section, for the paired technique, we would first erect girders 1 and 2, and then girder 3, and then move on to girder 4 and 5. So once we had all our finite element models created, we analyzed all of those models using the 4 different construction techniques. And we pulled out the maximum deflections in the vertical, radial, and tangential directions for all 120 bridges. We decided to look at the deflections instead of the stresses because we thought they would be a more global representation of what was actually occurring in the bridge instead of focusing on stresses in specific locations throughout the bridge. So we used an analysis of variance to examine the different influences of the parameters. So we used the ANOVA to determine which factors were influencing the deflection response the most. And remember, our parameters were construction method, number of girders, the radius, the unbraced length, and span type. So our initial ANOVA model included all interaction terms, which meant we had all of our parameters, and then we included our parameters times each other in a 2-term interaction, and then we included 3 terms interaction and a 4-term interaction. So we analyzed these, and through looking at the p-value results, we could determine what we wanted in our final model. And all the p-value is used for is to determine whether or not a factor is significant for predicting the deflection response. So we could analyze our model and determine which parameters we needed to keep in there to accurately predict our deflection. And another term we're going to be using when we go through some of the results slides is Tukey's method. Is a second test that can be conducted is to determine which differences are significant. And we'll use that a little bit more, and I'll explain it in a little bit more detail once we get to the results slides. So this slide is showing the ANOVA for the vertical deflection results. Now this was done for vertical deflections, radial deflections, and tangential. The vertical analysis provided the most useful results, so I'm going to go through those in detail today and just highlight at the end what we found looking at the radial and tangential results. So that top equation there is showing what we determined using our analysis of variance. We can predict our vertical deflection is going to be equal to the span plus the number of girders plus CM is going to stand for the construction method plus the R over L ratio plus we only have 1 interaction term, the span times the R over L ratio. And I should mention for our parameters we were looking at radius and then at unbraced length separately. But because our unbraced length only varied for 1 of the selected radii, we can combine that into 1 term for our statistical analysis. Because the unbraced length was conditional on the radius, the statistical model wouldn't operate with them being separate. So we just turned it into the R over L ratio, which is a very common term that's used in curved girder design. So some of the stats on this model that we got, you can see there, our R squared value is 79%, and R squared just represents the amount of variation in deflection that is explained by our equation. So of the 120 deflection results that we got, this equation can account for 79% of the variation. And the R square adjusted has just been adjusted for the number of factors in the model. So for the next few slides, we're going to go over some of the main effects plots and Tukey test results for vertical deflection, look at how span is influencing the vertical deflection and how the number of girders is, etc. And that table there is just showing that all the factors that we have included in our model have a very small p-value. That just means that all these factors are statistically significant in predicting our vertical deflection, so they should be included in this model. So this graph is showing the main effect on the vertical deflection of the number of girders. So remember, we only had two options in our study. We either had 4 girders or 5 girders. So you can see the fitted means vertical deflection for the 5 girder bridges is much higher when compared to our 4 girders. So this is just showing that the influence of the number of girders, if we have 5 girders instead of 4, our vertical deflection is going to be higher. So this graph, this is a little more interesting because one of the main reasons for doing this project was to determine the effects of our construction methods on erecting curved steel girders. So this graph, if you look along the bottom, we have our 4 different construction methods: paired inner, paired outer, single inner. And once again, the vertical axis is the fitted means vertical deflection in inches. So you can see, just glancing at this graph initially, that the single outer method, where we erect 1 girder at a time starting at the exterior radius, is resulting in deflection values that are a lot higher than our other methods. And this is due to the fact when you place that single exterior girder, it has a tendency to want to roll out. So by the time you put another girder up to stiffen it up, it is already rolled enough that it all keeps adding to that effect over and over again. But if you look at the paired outer results, you can see by erecting 2 of these girders at a time, we've increased the stiffness of that first section that gets placed enough that it's going to significantly decrease the deflection that we see. Now, if you look at the top of the graph, we have the Tukey adjusted p-value for the paired inner versus the single inner is 0.18. And if you look at the graph, you can see the paired inner and the single inner deflection results are very similar. And because our Tukey adjusted p-value is greater than 0.05, then we have to assume that the difference between the single inner and the paired inner is not statistically significant. So while it appears that the paired inner provides deflections that are higher than the single inner, based on that statistical Tukey value, we can't make a definitive statement confirming that. So the next graph, we're looking at the main effect, remember, on vertical deflection of the span. And you can see the single span results in vertical deflections which are larger than our 2 equal spans. And this would be expected. We expect higher deflections in the single span. Another thing of note, you can see there's a difference between the 2 equal and 2 unequal spans. However, if we look at our Tukey adjusted p-value, that's greater than 0.05. So we have to once again conclude that the difference in the deflections between the 2 equal span and 2 unequal spans is not statistically significant. Okay, now on this graph, we're looking at the main effect of the R over L ratio. And once again, remember, R over L is our radius divided by our unbraced length. So this provides some interesting information. The R over L ratio of 13.3, 17.3, and 20. Those are for the bridges that have the 300-foot radius. And then for the 13.33, that's our largest unbraced length at 22.5. And when we move to 17.33, our unbraced length is smaller at 17.3. So this graph shows moving our cross frames closer are going to reduce the deflections that we're seeing during construction. And looking at our 2-key adjusted p-values, our last two R over L ratios, the 23.13 is for when we have a 650-foot radius bridge, and the 35.59 is for a 1,000-foot radius bridge. You can see the bigger the radius of the bridge, the smaller the deflections we're going to see during construction. So this is just showing, I told you we did all these procedures. The graphs we went over in detail, we're looking at vertical deflection. We did the same thing for radial deflection and then tangential deflection. So this slide is just showing what factors we determined were statistically significant in determining each of those deflections. So for the radial, we found the span, number of girders, construction method, and our R over L ratio, so all four of our parameters, and then we had a number of interaction terms that were also included in the model. And if you look at the tangential deflection, the number of girders actually didn't affect the deflection in this case, but our other three parameters did, along with two interaction terms. So that last bullet, our construction method main effect, we determined that the single outer construction method statistically significant results in larger radial and tangential deflections than any of the other three methods. And if you remember, we found that also for the vertical deflection. Okay, so this slide, one of the other things we also tried to do, we had all this data from all these different bridges. We wanted to take a look at if we could possibly determine what we're deeming as the best or the worst construction method. And by the best, we're just saying that is the construction method that minimized radial, tangential, and vertical deflection. So deflection in all three directions. And worst resulted in the largest deflection in all three directions. So all 30 of our bridges were analyzed using all four of the construction methods. I'm going to present one case in some small detail and then a summary of results for all the other cases. So these are the deflection results for the 4-girder, single span, 91-meter radius bridge with an unbraced length of 4.6 meters. So all we did was look at the deflections. For the best, like I said, we picked the smallest radial, tangential, and vertical deflections, and then the corresponding construction method. And then the last three columns, we looked at the worst deflections. So you can see for this case, and this is, I should say this is rare, we had mixed results looking at this. But for this case, it's very apparent that the single outer construction method, it results in the highest radial, tangential, and vertical deflection, that it should not be used to erect this bridge. As for the method that minimized all our deflections, that varies. We had the single inner for best tangential and vertical, but the paired outer for best radial. So we did what we did on the previous slide for all of the different bridges. Now, these were the construction recommendations we made for the single-span bridges, and I should note this applies to what was looked at in the study. By no means am I willing to say that it applies to every single-span horizontally curved bridge that's being built. But based on the bridges that we looked at, we found that for the 4-girder bridges, for single spans, remembered that the paired inner construction method was the best to minimize our deflections. And for the 5-girder bridges, either the paired inner or single inner. The paired inner had the optimal radial deflections, and the single inner had the optimal vertical deflections. And another thing that came out of all these analyses was that for the 4 and 5 girders single span bridges, we recommended not using the single outer construction method. This method consistently resulted in deflections that were much higher than any of the other methods. So the next few slides I'm just going to go through briefly. We did the same and tried to make recommendations for the 2 equal span bridges, 4 girders and 5 girders, and the same for the 2 unequal spans. If you look here for this one, once again, pretty consistently, the outer methods were resulting in higher deflections, and the single inner or paired inner resulted in the best construction methods. But there is no single method that we would recommend for constructing bridges of this type based on our results. So now this is looking at the 2 equal span 5 girder bridges. You can see once again for the worst construction method, or the one that's resulting in the highest deflections, the majority of these are the outer methods. However, you can see the recommended construction method varies greatly depending on what actual bridge we're looking at. So this slide is the construction recommendations for the 2 unequal span 4 girder bridges. Once again, you can see the worst construction scenario method has a lot of single outer and paired outer. The recommended method, once again, is paired inner or single inner for most of them. And finally, this last graph, you can see we're seeing similar results for our 2 unequal span 5 girder bridges. So in conclusion, we used our statistical results to look at the different influences of the parameters on deflections of horizontally curved I-girder bridges during construction. We also took a look at the maximum deflections and recommended best and worst construction methods. For future research, it's hoped to expand these parameters to try to validate any of the trends that we were seeing. Some additional parameters that would be useful to include would be temporary shoring. That's used a lot during erection of horizontally curved steel I-girder bridges. And it's hopeful that somewhere in the future, possibly the AASHTO LRFD bridge design specification could include a section if you had a single span bridge with a radius that falls in this range. Possibly they could recommend or an erection technique that they would suggest that you would use for bridges of that type. So that's the conclusion of my presentation. I think we still have a few minutes if anyone would like to ask any questions. Okay, I'm not seeing any questions now, but I know the Midas people said if you have other questions to submit, you're welcome to, and we will look at them after the fact, and either someone from Midas or myself will answer them and get back to you.
Who's ready?
Okay, thank you so much for your presentation, Deanna. And if anyone has any questions, like you said, you can forward them to us, and we will take care of them. Also, if there's any specific that you want to ask Deanna, we'll forward those questions to her as well. So before we wrap up, I just want to go over our schedule very quickly. So as you can see, we have another seminar coming up next week on the numerical modeling and analysis training for response spectrum analysis. So for those of you who maybe missed the previous seminar or who are would like to have a recording of this seminar, we'll be posting the recording shortly. So just check your email, and we'll be sending the links out to our recordings very soon. So thank you again for making it out to our presentation. Oh, and also for those of you who have any questions about how to register for our seminars or who want to see the recordings, you just go to goodengineers.com. And you'll have full access to our seminar schedule as well as the recordings that we have posted thus far. So once again, thank you for taking the time to make it to the seminar, and we hope that you all have a good day. Take care now.